All right. Again, this is a sold-out class. I was expecting more people to be here, but I guess we're going to just get started. My name is, let's see, I'm going to do that. No, my clicker isn't working. There we go. My name is Vince Weston. I'm a technical evangelist. I work for Dell, and I'm not here as part of Dell, just here as being a mentor for teams. I've been working with various FIRST teams, FLL and FTC, for 10 years. So I've been involved in the programs. I'm glad to answer any questions you all have about stuff. My focus in the class today is to talk about programming with, I hope this is right, Android Studio. I've got to make sure I got the right class up because I'm teaching two today. So we're going to go through a bunch of the things about Android Studio. How do you, once you have a robot set up, a piece of hardware, and the XML configured to tie the hardware to the software, how do you then go through and program that to turn it into a running robot? Now I'm going to talk about a bunch of ideas. We're going to talk about the concepts. We're going to talk about, how do you approach it. We're going to talk about a number of details in the code. Know that there's a full sample of the code to run this robot. So we're going to talk today about teleop. We're going to talk about autonomous. We're going to talk about how to organize your code. There is sample code. If you use that QR code right there, which is also posted outside the room and will be on the last slide when we get done, you can go and get a copy of the slides from this today. You can get a copy of the code for the robot, the sample code. You'll be able to find a copy of the video for this class. So you don't have to take notes. There's no handouts. There's no tests. Well, there's one test at the end. Can you find the code? Right? But other than that, nothing else you have to do. So I appreciate you all showing up this morning and participating on this, and look forward to the discussion. At any point, if you have questions, just give me a shout. Put your hand up, do something. In general, hardware without software just sits there. Right? I mean, it's a very nice robot, doesn't do a darn thing. Software without hardware just kind of runs around in the cloud and thinks about things, but can't actually make anything happen. Tying the two together is really interesting. I was a programmer for many years and didn't touch hardware. So it was all software, managing data, putting out data, which I have to tell you is a lot less interesting than programming robots. Because when you program a robot, it moves. And whether it moves correctly or incorrectly, it moves. And there's something real that happens. And when you change it, it does something different. And so it's my favorite kind of programming. I don't get to do much of it, but it is a lot of fun. Most of the code in this sample was taken from the teams that I work with, because I'm not writing the whole code myself, right? I'm lazy enough I can steal from others. I hope you all be lazy enough to steal from me. But together, software and hardware make a good robot, right? You can achieve your goals. You need the right hardware, right? Software is not going to make your robot reach higher than the hardware can reach. Right, so you've got to have the right hardware, but the software can make it precise. The software can make it so that the driver can turn. It can make it so that autonomous actually works. It can make your robot achieve your goals. Right, so you control the motors for moving and lifting and doing various things. Sensors. During teleop, when you're driving, you don't need a whole lot of sensors. How many of you did FLL? Right, so in FLL, it's all about sensors, right? You got to follow lines, you got to find edges, you got to touch things. During the first 30 seconds of FTC, it's all about autonomous, right? The robot runs with nobody touching it. Unlike FLL, it doesn't come back to home and let you turn it, right? Once you can't touch it at all, you hit go, and it runs for 30 seconds unless you have to abort because it's going to break something, right? So it's a little different. The thing that I find interesting is that in FTC, you've got a 30-second autonomous. In FRC, it's only like 15 seconds, and you can actually remote drive it. If you want to, you can just put on a video camera and have the guy drive it. I think that's cheating. I think the 30-second autonomous is the toughest part of FTC. There's a reason it's worth, in a lot of games, you can wind up where there can be half the scoring, is what you do in autonomous. So autonomous is critical. And I think it's really great that the FTC program has that in there. It encourages you to really think about sensors. It makes them useful. In FRC, sensors are much less useful. Come on, guys. Plenty of seats. And we are recording this so you can watch everything. So sensors are critical so your robot knows where it is, right? If your robot doesn't know where it is in the world and doesn't know what it's touching, it's going to have a really tough time doing anything useful and autonomous. The software has it all together. You can make it easier for your drivers. For example, if you need to lift something up to a given height, you can set up the hardware and then run the software and say, run until I get to this height and then stop. Right, so the driver's not holding the button. Oh, I think that's right. Wait a minute. No, not okay, right? During competition, your drivers are going to be rather stressed. When people are stressed, they don't think so well. Right? You can also do things like, gee, it's almost endgame. Put a flag up on the side of the robot that says, hey, it's 45 seconds left in the game. Guess what? In 15 seconds, it's endgame, so go get near where you need to be for endgame. Right? Because they will forget, and then the endgame buzzer will go off. It's like, oh no, I've only got, and then they don't get things done, right? So you can do things to remind people. You have a timer built in. You can put flags on your robot. You can change LED colors, right? There are things you can do to give feedback. And all the autonomous is all done in software, right? So that's kind of important. Everything you're going to do is written in Java, and people say, well, okay, what's Java? Java is essentially something that's derived from C and C++. It's not some big scary thing. It's reasonably close to even basic. If you can read some simple statements. Come on in, guys. Just try and be quiet. We're trying to go through the material here. So the C++ is not that unusual. We got a bunch of seats down front here. We got some over here. Come on in, make a hole. Go ahead and move over to the end when you get in. And watch that one table. Thank you. There's a couple more seats there in the second row. So programming with C Java is not that hard. There's lots of books out there on C and C programming. There's lots of videos available. If you just get the basics and get started, I think you'll get very comfortable with it. Again, that's why we're giving you sample code. You can take the sample code and go play with it. So you don't have to start from scratch. You can start from code that pretty much runs a robot, and then all you have to do is change it. And if it's broken, you go back, right? Which is why you make backups. We'll talk about that a little more too. So as long as you have some basic understanding of the basic language, C, C++, you call it Java, whichever, you can take the code we're giving you and modify it and make your robot do some new things. Right, so we'll give you sample code, and that's what that's all for. You will have a driver station. The driver station, it's over here. Driver station is nothing scary. It's a phone connected to joysticks. Right? And so all you do is you get a couple Xbox controllers. All you do is turn on the software on the phone, hit some software settings to connect it up, and you drive. You decide what all of these buttons do, right? Just like the folks who write real games. You can also change them. So normally there are two drivers. We usually have one driver doing like the treads, the primary drive system, and the other one manipulating all the arms and looking for things. So you all figure out how you want to drive all that. But the driver station is pretty easy, and we will turn this on at the end of the class and let you look at that. Know that the driver station program that runs on that phone is something that comes to you from first. You cannot change it. Running a different driver station is reason to be ejected from an event, right? It's not a warning. It's not a we don't like that. It's a you're gone, right? Don't do it. Run their code. Be happy. We'll talk about how to do all that. Robot control, right? There's a robot control program that runs on the phone on your robot, and it's what drives your robot. So there's a structure that Revit and First have set up that drive everything else in the background. You have some simple things that run in a folder called theme code. Don't touch anything else. Right? You can try and go out and change other things. You're only going to get yourself in trouble. Stick with what's in team code, and you'll be happy. This understands the hardware. I mentioned earlier there's an XML file. We'll go through that in the hardware class that I'm doing next door after this if you want to come to that. Or you can watch the video of it online later. But the XML maps the hardware to the software. The code then can manage your wheels, right? All your motors for lifting, all your sensors, whatever you want to do, changing LEDs. Moving servos, and we do have sample code for all of that. So how do I do this? Right? We've assumed in this class that you may be your first year in FTC, you have no idea how any of this works. So we tried to make this pretty simple. Right? Download Android Studio. You can go online and find it. You can open up these files. Again, there's a QR code that's on the doors, and it'll be on the last slide here. You can go to the blog page and just click to download these PowerPoints. It'll walk you through the whole thing. This is also in the instructions you can get when you download the code from GitHub for FTC. So you download Android Studio, start that going first because that takes a while. Grab the latest code from GitHub for FTC. How many of you use GitHub? Any idea? You know what we're doing? Okay. Yeah, but pretty much you all know how to use the web. Go to the website, grab the code, do the download. Do not create this as a branch of the code. You don't want to upload your details back into the repository, right? Download it, unzip it. It's yours. It's private. Be happy. Then you work. That has everything set up, and there's a team code folder under it. You fill out the team code folder. When you are ready to refresh the code from GitHub, you download a fresh install of this, and then you copy the team code folder into the new release. Right? So if you never modify anything outside the team code folder, every time you need to refresh this because there's a new version, you just copy the folder and you're done. Right? You do anything else, you're going to make it a mess. So leave it where it belongs by default, which is right there in team code. Name your stuff. There's a doc folder that comes with this. It has documentation on how to set up phones. It has documentation on a bunch of the features. It's not going to give you documentation on everything. Some of the documentation of what do the function calls do aren't great. You'll find better doc just opening the pieces up in Android Studio and say, go to the definition, where is this build, how do I do things? But there's a doc folder there that'll help you. And again, you leave your stuff in the team code folder. There's a document that talks about how to set your phone up. When you get the new phones the first time, you've got to put them in developer mode. By default, Android phones won't allow you to just plug it into a computer and download programs, right, APKs. So you have to go in and go into the settings and click on the thing 10 times. It says, okay, you're now a developer. And again, that's all in the docs folder. And then once you've done that, you can push things to your phone. And then you create the software. There's an XML, and again, we talk about that on the hardware side. When you build these XML files that map the hardware to the software, by default, you build that on the robot phone. Back it up. Right? You can download it to your laptop. Do that. Then you have a copy, because then when your phone dies, or you want to change phones, you want to do something else, you can upload the same XML and not try and recreate it. Because if you recreate it, guess what? It's not going to be quite the same. And your program's not going to run quite the same. And you're going to spend hours debugging it. Trust me, we've done it. So make a copy. Only use one app on a phone. So you will notice that you can have a whole bunch of apps on an Android phone. You can have all kinds of things on these phones. Don't. Right? Take what they come with by default, delete everything you don't need, and install either the driver station or your robot control. Both of those applications, whenever something's plugged into the USB port, want to take them over. If you have both applications on the same phone and you plug this in on your robot, guess what? The driver station code on that phone is going to try and wake up and take over the USB port instead of your robot controller. And if that happens in the middle of a game and you can't touch the robot, you're standing around for the rest of the game twiddling your thumbs. Right? So don't install two things on one phone. It's either a driver station or robot control. Don't do both. Right? If you'll notice the phones that I borrowed from the 11347 kids, right? Here's a team number, driver station. Right? Driver station, robot controller, they're separate, keep them that way. There's a way to get into, within Android Studio, you can get into ADB. ADB is the Android debugger. The only thing that you should be using the debugger for the kind of stuff you're doing is for grabbing the XML files on and off and maybe pushing some code to the robot. If you're using Android debugger to really debug your code, you're really writing some funny code. You shouldn't have debug things that are causing code to crash. Right? And if it is, you should be creating enough comments in the log that you can figure out what's going on. There is a file. If you look under the dock applications, there's a driver station release APK. That is the driver station code that runs on your driver station. So you don't have to go to Google Play and try and download anything. Just take your driver station phone, plug it in, and run adb install and the full name of the file. Right? That will install it on that phone and you're done. And you don't have to worry about whether it's the same version you're getting out of Play that you want to use with your programming environment, because you downloaded it with the programming environment, so it matches. And having it match is a really good thing. Skip the default robot control program because you're going to write your own. Look at the XML and we can talk about that, but there's a ADB you can use to push and pull. So you can pull the file from the robot. So when you've got the robot control phone plugged in, you can read from SD card first, right, whatever your config name is, .xml, and you put it right, current directory. And then when you want to push it the other way, ADB push your XML name /SD card /first, right? Those commands will take the XML file. Don't worry about that. It's documented everywhere. You can see it. It's actually even documented in the sample code. When you get to the point of configuring and reading the hardware, there's a note in there about use ADB to do this, right? It's something you can figure out fairly easily. It's not that complicated. But this is how you're going to save that XML and how you're going to make sure you can push the same XML to the phones. That also means don't save old XMLs on the phone. You can save them on your laptop, delete them off the phone so you don't use the wrong one, especially in competition. There's also a self-inspect on your phone. So when you have two phones plugged in and you're trying to drive your robot, before you go to any competition, you should run the self-inspect. And the self-inspect on each phone will tell you, yes, my phone is correct, I have Wi-Fi turned on, but I'm not attached to any other Wi-Fis, I'm only doing Wi-Fi direct, I don't have cellular enabled, I'm not doing Bluetooth, right? All the settings are right. There's a very nice little checklist, it's a one-page checklist, and it's either all green or it's not. If there's any red X's, go fix them before you get in your competition. It's a whole lot easier, because if you show up with red X's, and we say, well, that means you've got to go change this, and that thing you've got to change isn't how you were testing at home, guess how you're going to do in competition, right? That's not what you want. So check it up front, at home, easier to do. Hardware mapping. So these are the definitions in the code. You will at some point come up and say, gee, I want to map hardware. In fact, I think I'm going to flip over to Android Studio to show you how that looks with Android Studio. Yeah, I accept. Let's see, is that big enough to read? Maybe not. Let's see if I go. I'm just realizing that's kind of tiny, but I'm going to try anyway. This is not the core. Sorry. So in the code, we do things. We define DC motor, motor left front, motor left rear, and those kind of things. So you define what your motors and your servos and all are. And again, you guys are going to get copies of the code, so it doesn't matter a whole lot. But I just wanted to show you, right, there's a comment here about how to go grab some things from ADB push, ADB pull. So you say motor left front equals hardware map get, and you have something in quote left front, right? So what that says is go read the XML, figure out what I put in the hardware map that says left front, and map that to the software instance that I call left front here. All right, so this is the mapping. This is how you bring the hardware and software together, is by using the XML files and these hardware discoveries in Android Studio. And again, we're going to give you the sample code so you don't have to worry about it a whole lot. Once you've done that, all right, you map your motors, you map your sensors, you map your servos, all those different things. You may also want to build basic drivetrain stuff. And for those who are taking photos, we are giving you copies of all this stuff to take home, so you don't have to live with photos if you want the real slides. But for example, on this robot, we have a move robot. Right, really simple command, move robot, the speed for the left, speed for the right, go. Right, so it's pretty simple. But the reason we built move robot into the core is so that autonomous can call move robot, just like teleop can call move robot. And if we need to fix something about how the robot's moving, it's fixed in one place and everybody shares it. Right, so a lot of your basic drivetrain information, if you have a lift that needs to be manipulated, if you have arms that do special things, all those kinds of features, if they have more than a couple of statements, if it's more than like move a servo to some setting and pull it back, you can just set all that up right in your core, figure out how to manage your hardware. We recommend that you use classes. So a class is basically just a way of describing a set of features. So for example, we start with a core class that goes and documents all of our hardware, that sets up the drivetrain, that makes all those things work. And then we extend that into additional modes. So we say, well, gee, I'm going to now make a test mode that has everything the hardware has, plus I know how to interact with a joystick to do motor testing or servo testing. I'm going to build an autonomous that knows how to do the base, plus it knows how to do autonomous things. And then I'm going to make an autonomous that knows how to do, that knows how to start with certain settings that uses all the autonomous code. So we'll talk about how to extend with classes in a second. You should have a test mode. Right? So everybody says, yeah, I'm going to have teleop, yeah, I'm going to have autonomous. Why do I need test? If you've been competing all day and you replace one of the motors in your drivetrain, let's say you have a Mecanum drive, 4 independent motors that do things. Right? If you replace that motor, how do you know if the motor is moving in the right direction, doing everything it's supposed to do? I mean, yeah, you can put it on the floor and try and drive it and see whether or not it works. But the easiest way to debug it is set it on its side and test the one motor that you changed, right? Make sure that it moves the direction it's supposed to move when you say forward, backward. Right? So have a test program that will allow you to test individually each of your motors, each of your servos, that will do the things you need to do so that you have a way to debug things. There's nothing quite like replacing a motor, putting it back on the field for a competition, and it goes completely haywire because you have flipped polarity or did something else silly. Right? The servos, some of the servo wires are not keyed very well, so it's easy to put them in backwards. You put the wire in backwards, the servo doesn't work. So it's good to know those kind of things. Got to have teleop, got to have autonomous. And we'll talk about how to set some of that up. So again, I kind of talked about the way the core is your hardware mapping, and then you derive from that the test and the teleop and the autonomous, and then from autonomous we derive blue and red and such. And so let me just show you quickly what I mean by that. So back in the code, in the autonomous code, expand all this. So in the autonomous code here, we have the start of a class. So we declare rev tank auto. Right? There's a rev-based robot. It's a tank drive, so rev tank is a pretty simple name. The autonomous, right, extends the rev tank core, but we don't have a way to actually call it. This is how we set it up to be called in the driver menus. And then it defines all the autonomous states. So in autonomous, in this example, we have, right, states for I want to move, yeah, I'll just leave it. But I'm done, I'm starting, I'm gonna bring my lift down, or I'm gonna move the robot down, I'm gonna move forward, I'm gonna turn, I'm gonna move again, I'm gonna stop, right? We have a set of states that we can be in. And so we define all those, and we have all the code in here for autonomous to make all that work. And I don't know if you all have ever heard of a state machine or played with it, but basically what this does is every time you go around your loop, it basically goes through the loop and it says, okay, what am I doing? I'm doing tank start. Well, then I need to do these things, and then when I'm done, I'm going to change to a new state. Oh, now I'm doing tank down, so now I want to set my servo position and move my motors and do whatever. Right? So you go to different states, and then as you make each state change, you can set parameters in this for how long do I wait, or what do I look for before I start the next state. Right? And again, you get all this code. It's available to you. It's documented. I won't say it's well documented. You get it. It's free, so it's at least worth what you paid for it. So you get that. Now you've got an autonomous program. What happens when you want to do blue or green? Do you want to write the same code, 5 or 6, 7 times, right? What if you have an autonomous for red and autonomous for blue? Oh, I wanted to put delay in both the red and the blue. Oh, I want to be able to turn left or right. And I mean, pretty soon you can have 12 different autonomous programs, and now you're trying to edit updates in all of them. So what we set up here is another one. This is auto blue ground, right? And all it does is say, am I red is false, right? It's a global variable we have to say you're red or blue, right? My delay is 0, and at the start, am I hanging or not? I set that to false, right? So I am blue, I'm on the ground, I'm not delaying. That's all this does. And then it just calls the other autonomous. So we call this a derived class. So essentially, this is the same autonomous, we're just setting a couple of variables. Right, so this allows you to have as many versions of starting autonomous as you want. So you can do red, blue, delay, no delay, turn left, turn right, whatever you want to do based on your game for the year. But you have one real autonomous program that you maintain, right, instead of maintaining lots of pieces of code. So it's, again, you got samples of all this. It's pretty easy to do. And I'm sure you'll have some questions. You all can also reach out to me. So that's the complicated part in Android Studio. But you have this ranking, this hierarchy, right? These are all derivatives of auto. That makes sense? Questions? Am I totally crazy? Well, yes, I'm crazy, but that's another story. All right, the other thing you should know is that if you're doing this with the Rev Hubs, you've been given a gift. In every Rev Hub, there's a really simple little Bosch sensor that is a 9 degree of freedom inertial management unit. So it tells you your velocity, your acceleration, and your current heading in all 3 dimensions. And you can use gyroscopes, right? It's essentially a gyro to tell you how fast you're turning and how other things are going. That's nice. If you're going to do that, though, you have to say, okay, how long have I been moving at this speed, and kind of calculate where you're turning. One of the things that the Bosch IMU does is it has a heading for you. And you can just go into the Bosch and read and say, where am I pointed? And it'll tell you 0 to 360 which way you're headed, right? In autonomous, there is nothing like knowing to the 1 degree accuracy which way your robot's going. Right? Before this was absolutely painful. There was no equivalent, and there's nothing like it. The autonomous code does have this set up. One of the things it does is when you say drive, the last angle you told it to turn to, it tries to use the varying power on the wheels to decide how to drive forward, so it will auto-correct to drive in the direction you want it to go. So if it winds up that you turn and you're supposed to turn 60 degrees and you turn 55 or 70, right, as you start driving, it will straighten out and be going 60 degrees. Right? That makes up for a lot of slop and other things, means you don't have to worry about going as slow and precise making your turns, because plus or minus 5 degrees, who cares? I'll straighten out when I go. Right? So this is an absolute gift. Please use it. Again, we're giving you sample code to help you use it. You're welcome to or not, but it's great. There is a calibration code for it. I haven't ever had to use it, so I wouldn't bother a lot of time calibrating. Just know that it's there and you can. And again, the sample includes that for IMU guided driving. There's also a power sensor. And I point this out because, again, this didn't exist in some of the previous code. But when you have the rev controllers plugged in, they will give you your current battery level for your main power battery. Right? And why would that be important? Well, you should know that your power on your motors looks a little different at 100% when your battery's at 14 volts versus when it's at 11. Right? So we put a sample in the code that looks for, hey, am I over 13.5 volts? If so, do this. If not, do that. Right? Just kind of scale the power from like 85% to 80% or something. But you can scale your power by default for autonomous, just so you know how you're driving. In teleop, you're going to go 100% anyway. Right? But doing this kind of thing and playing with it in autonomous will help you to have a more accurate autonomous, because you'll tend to apply the same power to the wheels. Now, I'm sure you all can get really fancy and come up with awesome calculations to decide exactly how you should scale that power. Right? I'm not giving that to you because I haven't done it. I'm not doing that work. You all can figure that out. Right? You can go post it on the web and share it with everybody and try and get some points for everybody reaching out and grabbing your code and using it for the next season. Let's see, how am I doing? We're going fine on time. Okay. Autonomous, you need sensors. If you don't have any sensors, you don't know where you are. So you have the IMU to at least tell you which direction you're pointed. And theoretically, if you add up the time times the distance, you could figure out where you are on the field. That's a little complicated. You usually want to sense some other things. I will also say that several folks have used distance sensors, like if you're going to travel parallel to a wall, right, it doesn't hurt to have a little distance sensor poking out from the side of the robot looking at your wall, saying how far away am I? Right? Rev sells a new distance sensor that costs like $8. Right? And it works up to 200 centimeters, and it doesn't need things to be opaque, because the walls on most of these fields are transparent, right? So if you're doing just optical stuff, it'll go right through. So you got to make sure you choose the right pieces and plan for that, right? If your home field is not plexi, test it with some plexiglass or Lexan. Make sure it works, because if your home field isn't transparent, you get on a transparent field and your sensor goes right through it, you're going to be surprised. Color sensors can be important when you're looking at different things, depending on the game, right? Some games, color is important. Some games, size is important. Some games, there was one bowled over, there was a magnet sitting in the middle of one of the balls, and you had to figure out which ones were magnetic. Ring it up, some rings were heavier than others, and you had to weigh them and check, right? We just had a push sensor that did that. This is harder than teleop, right? You have to try and teach your robot how to deal with every situation that's going to come up. You will fail, right? The goal is to get good enough. You're not going to get perfection at this. You've only got 6 months or so before you get to the league championships. Actually less than that, right? January for league championships, maybe one in December. You only have so much time, and you're not going to have a robot for the first chunk of that. So know that it's not going to be perfect. Figure out how to keep it simple. And think about what your partner is going to do, right? You're going to have an alliance partner who is going to change during the matches of the day, right? How are you going to coordinate with them for what you're going to do, and how is your code going to be able to adapt? Because if they walk up and they say, well, my own robot only works this way, so you use me or you don't, right? At some point, if your autonomous is good enough and they're not compatible, you may just say sit, right? But you'd like them to do everything they can do, and that means you have to be able to stay out of their way. They have to stay out of yours. So think about what it's going to be like in autonomous with 2 separate robots trying to achieve the goals, right? That's going to be tougher this year, right? The game this year is tough for autonomous coordination. So you'll hear about all that in about 2.5 hours. All right, and the only reason I know about the game is because I'm going to be part of talking about strategy this afternoon. All right, so that's harder. Yeah, you don't. It's always interesting when your robot decides it's going to turn right, but it turns left, or it gets on something that turns at 90 degrees when it wasn't expecting it, and it kind of goes off in a crazy way. You do need to be ready to hit the stop button. You are allowed to hit the stop button to stop the robot from damaging things on the field, right? So if it's going to hurt someone or if it's going to break something, you're welcome to turn it off. If it's going to go somewhere you didn't intend and cost you a lot of points, you are not welcome to turn it off, right? Turning it off when it's not required for safety or protection of the field is a major penalty, right? 40 points gone, well, gifted to the other alliance. You really, really don't want to do it. So just keep in mind, it only runs for 30 seconds. Suck it up if it goes sideways. You're going to spend a lot of time on autonomous. That's also the reason you need hardware early. The autonomous guys need time to program it. So build some fundamental drivetrain and get it going quickly, because building autonomous the week before competition really hurts. Figure out your alliance color and all that. Again, set up an autonomous that'll understand that. Right, we got a state machine looking for a blue line, turning right, turning left, doing these things. You'll figure that out. You don't have to use the state machine, right? That's an example of how to do things. There are teams that write the code that's just a continuous, okay, I'm sitting here, I'm looking for this, okay, now I'm doing this, now I'm doing this, and they never break out of and go back to a loop. They just run continuously. It's a different way of doing the autonomous. You can do that, that's perfectly legal. I find it much more difficult to program because you can't adapt to what happens when I get to failing something. How do I go to some new state? But you're welcome to program it however you want. I've just given you that example. So teleop basically connects your joystick here to your drivetrain. It also gives you buttons for doing everything else. One of the things we found is having joysticks. Yes, those joysticks are analog, right? You'll understand the difference between analog and digital, right? So the analog, the joystick does -1 to +1, right? So you've got the full control. By the way, you'll notice X and Y do, or the X do what you think, right? Positive, negative, but the Y, pushing up on the Y controller goes negative, and pulling down goes positive. Completely backwards to how most of us drive, right? Tank, you push both forward, you want positive, right? So in the tank code, we actually flip those around. Just be aware of those kind of things. But you can also do things in your programming like, gee, my drivers tend to just hit full on all the time, and when they want to move slowly, they don't think about how to move just a little. So you can put a button on there, which we have for the test robot, that says, hold this button down and your robot will run at 30 or 40% speed. Right, so now you can move the joysticks and you can slam them all the way on and you still won't go flying across the field. And when you're trying to move plus or minus an inch, more than 30 or 40% power doesn't help you a lot. But talk with the drive team, right? The job of the coders in terms of teleop is to figure out what the drivers want from these joysticks, not what the programming wants, right? What'll help your team drive better? What can they do? Help them out. We've also had robots some years that need to go one direction with one side of the robot and a different direction with the other side of the robot. There's no reason you can't just have a direction flip button on the joystick that says the robot is now going the other way. So I push forward to go forward on the robot, and then I hit the button, and pushing it forward like that sends the robot the exact opposite direction because the other side is now the front. Right? So we've had times where some things last year, right, there was a lot of go pick things up out of the pit. Oh, wait a minute, now I want to drive backwards and put them in the crater, or I pick them out of the crater and put them in the lander, right? Or I need to go hang on the lander, so that's the front of the robot is hanging on the lander. Well, but when I'm picking them out of the crater, I want the other side to be the front, right? It's much easier for a programmer to make a button that flips that than to have the driver flip that into their head, right? Make it easy on the driver. So that's your job. Manipulator control, again, since you have two controllers, it's really nice to be able to have the second driver be able to manipulate things while the one person is just doing drivetrain. But talk to the drive team, it's up to them. If they're going to do just one joystick, and they're going to drive everything, one person's going to drive the whole thing, great. Right? They can do that. Just talk with them and help. Again, the job of the software is to make the drive team successful. And then you can use sensors to set up lifts to go to certain heights, or to detect colors of things, detecting magnetic balls, again, weights of rings, whatever you need to detect. Timers to set off a flag, again, ready for endgame, whatever. Lots of things you can do to help the drive team be aware of what's going on. Again, how do you give them feedback, right? What's going on in the robot? So if you're sucking things in, and when they get all the way in, you're done, right? They may be doing that on the far side of the field. It may be 12, 15 feet away from them, right? Can you have a flag go up that says, hey, I was trying to suck something in and I did it, right? Stop bringing things in now and take it away, right? Or in the last year's game, right, suck in 2 and you're done. So get 2 in, you can have a flag go up in case they can't see it. Yes, I sense it. Yes, I've got 2. Go do something else in case they can't see it. How can you help them? You can raise flags. You can turn on lights. There's a nice LED control that Rev makes that I haven't played with yet. But there are things you can do to control LEDs, so you can have fun with that. Think about what the team's going to do under the stress of competition. When you're practicing at home, turn on some loud music and yell at them, right? In a defined, you've got this time frame go, right? You've got the 2 minutes. Do the full test. Do the 30 seconds autonomous. Uh-oh. Can you hit the light switch behind you? Yeah, the other one. Thanks. So think about the fact that they're going to need to test that. Set up some test conditions where they try driving under stress, right? Yell at them. Yell unnice things at them while they're testing. Get them stressed, because that's what they're going to have during match competition. There's going to be a lot going on. There's going to be multiple teams yelling. There's going to be alliance partners. There's going to be opposition. You can do scrimmages. The good thing about the league format that we're in Georgia is you're going to have at least 4 meets to go to, each of which you get at least 5 matches. Right? So before you get to your league championship event, you're going to have at least 20 matches where you're doing things with different teams, and they'll be stretched out across more than a month. Right, so you've got some time to adapt. You don't need to do as much stress testing on your home field, but be aware of it. Think about how you help things be like they are in competition to learn. Right, what feedback do they need? Ask them. How many of you know what a postmortem is? Right, you go after the fact. You go and ask what happened. So after a run on the field, right, the best thing you can do is go back to the pit and say, okay, what worked well and what didn't, and somebody actually write it down, right? Because you will forget. You're going to do 5 matches that day, and if you ask, you do that on Saturday, and if you get together on Tuesday afternoon and say, hey, what worked really well in match 1? Yeah, those French fries were good. Right? Not going to remember details. You need to do it right after the match. Right? Same thing the military does, right? You do a flight op, you do any other kind of operation, the next thing you do your debrief, right? What happened, what worked, what didn't, what do we improve? You want to do that kind of thing in matches especially, right? In your practice in the room, it's pretty easy to look, see what happened, make a couple notes, modify things. But in competition, there's nothing like doing that debrief afterwards. All right, you're going to try some complicated things. You will have to find new ways to move robots you're going to design, whether it's an ability to lift a robot up or to lift particles up or to throw something or to grab something. I guarantee you're not the first people to approach this kind of a problem. Look around on the web. There are no bonus points for figuring it out again. Someone else has already done this. Figure out what they did. You may improve on it. But if you're figuring the whole thing, if you're just sitting in a room with not looking at anything, thinking about it just as your team, you're missing out on a whole world of engineering expertise. Yes, you should use your mentors. You should also use YouTube and other ways to do research. Right? The kids from Wheeler, the 11347 team last year, built a swerve drive, right? All 4-wheel swerving. They came up with some great ideas for how to build the hardware inspired by another team they saw. They also went out and found a FRC team that had written code to do a really nice job of managing a swerve drive, including an Excel spreadsheet that let you see, as you change variables, how are the wheels going to point, right? And you could plug in your calculations and your code and see if it was going to work, if your whole robot was going to blow up, before you put it in hardware, right? That was an absolute gift, right? It was well worth spending half an hour looking around the web trying to find things, because creating that in Excel would have taken much more than that time. Right? And then they had sample code and a whole bunch of ideas and the basic calculations. Don't do these things from scratch. If you have something hard to solve, go look for help. Even if it's just how to use a lever to move something right, think about where it's been done. Go look for examples. I will also say that shortly after kickoff, you will see things on the web. There's a team that tends to build a robot in a day, or robot in 3 days, depending on how ambitious they're getting. But they will take this year's competition for FTC, and the weekend after the launch, they will go spend a number of hours building it. They will put up a video of what they built on YouTube. Done. Right? And that's not to say this is the way to solve the problem, but they may have thought of things you're not thinking about, and it doesn't take long to find it and look at it. Go look. Find ideas. If you're thinking about drivetrains, there's a drivetrain class going on down the hall right now, so you missed that one. But look on the web. Look at the winning teams from last year. Think about if that would work for you. Right? Yes, you can use Mecanum. Yes, you can use Tank Drive. You can use the standard bots that just have swerve in the middle. You can use the actual swerve drive code that's rather complicated. Right? There's lots of options for how to do things, but don't try and do them all from scratch. If you have a big problem you're trying to solve, break it into pieces. Right? Don't try and solve everything about your robot at once. If you're going to do a swerve drive, build a swerve drive base and nothing else. Right? And build other attachments separately. Don't try and put things together until they need to be put together. Think about how to keep it simple. And by the way, we're having a whole strategy discussion after the field reveal. Right? There's going to be a reveal. You can go tour the field, and then afterwards we're going to talk for a couple hours, if you want to, about strategy on what you might do about this year's game specifically. Right? So feel free to come to that. Consider the control software, right? When you're exploring this, if you've got hardware you have no way to control, right? If you have a lift that goes up but you don't know where it is, or you can't make it stop before it breaks itself, probably want to put a sensor somewhere so you can know where you are. Probably want to put a limiter somewhere so it doesn't break itself. Right? How do you control it in the software? Be thinking about that as you implement. And again, ask your mentors for guidance. You've got mentors for a reason. There's lots of mentors available. GE and Lockheed and a bunch of other companies are local and have folks who are generally glad to participate. And as a bonus, a lot of them, after they show up and talk to you, can get their company to write your team a check. Right? Lockheed and GE in general, if you have a mentor from their company working with your team, the company will write you a check of $500 a year. Right? Just as, hey, we're here to sponsor you, so you're getting expertise in engineering and you're getting money at the same time. Right? It's true for a lot of the large companies. Can't get Dell to do it at the moment, or I'd be offering people money from my services. But Lockheed and GE have been doing that in the past, and there are others too. So what else? You will write bugs. Right? There's a very cute video. A guy said, his 5-year-old daughter's talking, what are you doing? Well, I'm taking bugs out of my code. She said, well, wouldn't it be easier not to put them in there? It's like, well, yeah, but you're going to, right? You will have bugs. So the way you break things down, the way you put comments, the way you send debugging information into the log, and we do have some logging functions in the default code, right? Yes, I'm doing this. Hey, this is my current setting. You can look on the phone, right? On the controls, on the driver station, you can put anything you put into certain log values will show up as text on the bottom. So you could say, hey, I'm in this state, right? It's one of the things our code does. I'm in this state. I'm setting my motors at this power. I'm sending in this direction. I'm reading this from my joysticks, right? All that can be there on the phone. So when you're looking at the field, you're like, well, that's not right. You look at the phone, it's like, oh, yeah, no, I think I'm somewhere else, right? It helps with debug. The more your code gives feedback to the people who are driving it, the easier it is for you to figure out where something went wrong. So be helpful with the debugging. It doesn't take extra time. Hardware will fail, right? Can your code adapt? Now, if you're running a swerve drive and one of your swerves goes wonko, you can't really adapt. You're dead, right? But there are some things you can adapt to. If one wheel isn't working right, maybe you can apply more power. Maybe you can figure that out. Right? Are there things you can adapt to in the code if a sensor's not working or whatever else, right? If you're doing distance readings on sensors or some of these others, you will sometimes see, oh, I'm at 20 centimeters, I'm at 19 centimeters, I'm at 200 centimeters, I'm at 18 centimeters. Right? You will occasionally get some bad values. How do you deal with those? How do you adjust to the fact that the sensors, because they're on a robot that's bouncing around on a field and hitting things and doing things, you may get some values you're not expecting. So how do you deal with that? By the way, one of the things you can use that internal management unit for is it has a gravity pointer, right? Which way is down? If down isn't the bottom of your robot by a significant amount, you're climbing on something, or you're being tipped by something. You may want to stop. Right? If you're climbing up the wall, it's much better to stop. We watch robots climb up and completely tip over, and then they're dead for the rest of the match, right? Remember, in FTC, starting last year, there is a 8-second timer that counts down between autonomous and teleop, but there is no stop. So there's no point at which it is safe for any of the referees or FTAs to go onto the field to work on a robot or set anything up. So they won't. Even if they can reach it from the side, theoretically, they are specifically not allowed to in the rules. If your robot turns itself over in autonomous, it will stay turned over until you fix it or the match ends. So having a gravity sensor that says, oh, I'm tipping up, I should probably stop. Not a bad thing built into the robot. Right? If you're doing autonomous loop, it wouldn't hurt to have something that just looks and says, hey, while I'm checking for things, if I'm tipping up, just stop. Right? Give up. The challenges will keep coming, right? Writing the perfect solution will take a long time. Write something that's reasonably good, use it, test it, see how close you are. Because if you think you're going to write the perfect code, you can spend 2 weeks writing code only to find out that your concept was wrong. Right? Get something started, get it on the robot, go try it. Again, one of the beauties of this is you're coding for real hardware. You actually get to see it run. Do yourself a favor, go see it run. Right? Which also means you need a robot to work with, robot build guys. Right? Build a drivetrain, build a part, let it be tested early with software. Also think about documentation, make all of it clear. If you don't write comments with your code about what you're thinking, when the next programmer comes along because you're out sick or whatever and they've got to fix something, they might fix your code in a good way, they might just rewrite it, they might just break everything. Documentation is good. It will also help you to remember, right, what you did. So, getting close on time here. You need code early for practice. The drive teams need a chance to get used to driving. You got to test autonomous, right? That also means you need a robot. Put things in, group them together in ways that make sense so you make it easier to manage. You got to build hardware and software in parallel. Your drive teams or your build teams are going to want to build a lot. You should consider building 2 copies of your drivetrain, right? So that the drive guys can be driving one around, and the software guys can be programming autonomous movements, right? While the hardware guys are busy putting attachments on the other drivetrain. Because they're going to be spending a lot of time build that. Oh, that didn't quite work. Wait a minute. Oh, wait, that right. And the drive guys are sitting around with you. Well, I mean, you'll have some sharing, right? Different people doing multiple jobs, but it really helps to be able to test the drivetrain and driving and all that while all the hands are in the robot. Because you'd think that they're going to be done with that hands in the robot thing early. They're usually done at least 30 seconds before the first match starts. And mostly because they're tools you can't bring to the match. So plan for programmer time with a dedicated robot, plan for drive time, team time with working code, plan to make lots of versions, back them up, save them. You will change a lot of things, so think about that. Things will break, hardware will break, software will not do what you expect. Have backups, have copies, right? Do you test for things that shift, right? If you have belts, can they get loose? Right? If your drivetrain has special things about it, do you have a way to test it and make sure it's okay? You need some easy ways between matches during the day where you've got like 5-10 minutes in the pit. Can you check and make sure everything's good to go? You don't want to figure out it's not good to go by putting it on the field and you're in the middle of the match and it's not working, right? And anything you can automate is a good thing, so do your best to automate it. Documentation. If you come up with a really cool idea, don't bother to do I mean, you're going to put things in the notebook and all about it that day, sure. But don't make separate documentation somewhere else as like a software piece of stuff. Put it in the code. Just put comments right in the code. Hey, this person was working on the code on this day, came up with a really cool idea, and it works. Or, hey, we came up with a really cool idea, we tried it, and it failed miserably. Right? But document it in there, because then you can share it with the folks who are building the notebook, and you can actually get your notebook to reflect the journey on the software. You're also going to put a copy of your software into your notebook, so at some point this code is going to wind up, and just like all the pictures you've got in the notebook of the hardware build, this will kind of give some of the history of what did you do in software. If there's no comments like that, they don't know that you just didn't download the whole thing off the web, right? And if somebody says, hey, I did this, the judge can come talk to you. Hey, what did you think about it? Well, I tried. Right? It gets an interaction. It kind of documents your code as yours. If there's something not obvious, put comments in. Make it obvious to the person who comes behind you. Backups. Extra copies on your same laptop is not a backup. I mean, it helps. But if that one laptop dies, you're in trouble. We have seen many teams show up to competition where the laptop just died. Right? Nothing. At least put it on a USB stick, share it into the cloud, do something, make it easy. And check for the updates in the first repository, so go to GitHub, check for the updates. You don't want to show up at competition and we say, yeah, the new rule came out last week, you got to be using 5.2. Did you not download that? Right? Oh, by the way, it breaks these 3 things that are key in your code. Right? The time to find that out is not at competition, so do it early. We do have a couple of resources on Slack. There's a coaches and mentors section as well as general resources for anyone on the team. If you're interested in that, send me an email. Glad to get you participation in that. That was not heavily used last year by the teams. But if you want to share things, we're glad to facilitate that. And again, there's a QR code here. Feel free to reach out to me. The QR codes are also on the wall. And we are at 10 o'clock exactly. So I'll take 2 minutes of questions before we got to move rooms. Yeah.
Wait, where can we find the slideshow?
Where can you find what?
The slideshow today.
Download it with that QR code. That points to a web page. So that's a blog page. The QR codes are also on the wall outside. That gets you access to the code. There'll be this video, the video of this class. One other thing for those of you who are about to do hardware, in case you're not going to the hardware class, this year there will be no flags on the robots. Your alliance will be determined by a symbol that goes with your number on the side of your robot. You will have a red square option and a blue circle option, and you will deliver both. You will be able to flip between red and blue. So there's a PowerPoint out there you can grab that's a one-slide version of this that you can just cut up and make into something. I mean, it's covered this in tape, right? I'm not saying this is the great way to do it, but you need something to get you legal for the first match. This will get you legal. All right. Thank you all.